What do you think about this, lab, Kenzie? Is there a way that a liquid could defy gravity?
Well, it doesn't make sense if it does. But if we're assuming it does, maybe the denser a fluid is, the more force that will be on the lid, and then it could actually overcome atmospheric pressure. Okay, so today we're going to use the knowledge we have accumulated from fluid mechanics, and we're going to use some mason jars and a few other liquids to see if a fluid can defy gravity. Okay, for our lab experiment, you will need a mason jar and a mason jar seal. You'll need around 3 mason jars. And for the fluids, you'll need we are going to use molasses today. We are also going to use some water. And then we are also going to use oil. And the last but not least, vinegar. And to record all your data, you're going to need a piece of paper, ruler, and pencil.
For this experiment, you're going to need to record the radius and height of the mason jar, assuming that it is a uniform cylinder. You're also going to need to record the densities of each of the fluids that are used in the experiment.
Okay, just to compare before we begin, we want to show you what happens when the mason jar is upside down with no fluid in it. So you put the lid on, then as I let it go, there's nothing holding it together and the lid will fall off. Let our water sit for a while so it was around room temperature. We're pouring the water in the mason jar to the very, very top to where the surface tension makes the water bubble over. Just a little bit, yeah, like that. Okay, and then we're gonna put the lid on. So the lid isn't really pressing, it wasn't sealed on, so how does that work? So what happens if we try to take the lid off? Okay, so we're going to test different densities, so different fluids, and we're testing vinegar next. So she pours the vinegar into the very, very top of the mason jar. And does the same procedure as the water, puts the lid on and brings it over and holds it upside down. Next, we are going to test oil, which will have a higher density than the water or vinegar.
Slow.
So next, we are testing molasses, which has the highest density of the liquids we tested. Okay. So, you may have seen this phenomena. So why does this occur? Well, you see, when I have it to the water to the very, very top of the lid, there's nothing in this jar besides water. So when I put this lid on, and I turn it upside down, all the time, all around us, there's pressure. There's pressure from the atmosphere, and at every given moment, it is pressing on every single point of this jar. And because there's barely little to none within the fluid, there's nothing pushing the lid down. So the pressure, atmospheric pressure, is 100 times 10 to the 3 pascals, which is much, much greater than any of the pressure that pushes down the jar from the fluid. And pressure can be talked about as a force. That's why we are talking about pressure pushing it down. But if I slowly just add a little bit of water, or like let the water fall out and add a little bit of air inside, that air has atmospheric pressure. And right now it doesn't affect it because as of this point it's still in equilibrium. There's too much water for it to bug. But if I keep adding a little bit of water, it'll eventually overcome and the pressure will push it all down. Science.
In our experiment, we found that the pressure from the atmosphere was greater than the pressure created by all the liquids that we tested. That's the reason that the lid stayed on for all of the different experiments that we performed.
All right, now let's do some calculations for the forces acting on our experiment. So first of all, we have our mason jar here. It had a height of 13 centimeters and a diameter of 6.4 centimeters, so a radius of 3.2 centimeters. And here is a free body diagram of what was happening in our experiment. So I broke it down into two forces, the force down and the force up. So the force down consisted of rho GH times the area of the jar. So that's the pressure created by the water and times the area of the jar. So that would have been the force created by the water, and then that would have been, and then plus the mass of the lid times gravity, and then the force up is going to be the atmospheric pressure. It's going to be the atmospheric pressure times the area of the jar. And here are some of the densities we used for our experiments. So we had water, molasses, canola oil, and vinegar. So first of all, I'm going to calculate the force up, as it's going to be the same for all of the experiments. And so the force up is going to be, like I said, 1 atmospheric pressure times the area. So that's 101,300 pascals and 0.032 meters squared times pi, which is equal to 325.88 newtons. So quite a lot. And then the force down is going to be equal to 1,000 kilograms per meter cubed times 9.81 meters per second times the height of the mason jar, which is 0.13 meters, times the area of the mason jar, which is only 4.10 newtons, so not a lot. Obviously, the force down the force down would also be have the normal force of the jar, so that's why otherwise the lid would just fly through the top of the jar. So there was the normal force acting it down, so that's what just kept it stable, but that's kind of given. Changing the densities of the different fluids, molasses was 5.49 newtons, canola oil was 3.77 newtons, and vinegar was 4.14 newtons. So all pretty insignificant compared to the amount of force that would be required to make the lid fall. So now, on the next sheet here, we did some calculations just for fun to see how much or what would be required to make the lid fall. So to make, if we kept all the variables the same and we used the density of water, how high would the mason, or how tall would the mason jar have to be for it to fall? And it would have to be 10.33 meters. So that's really tall. Now if we kept all the variables the same and we changed the density, and we found the density that would be required, so the same mason jar, how heavy would have to be the density of the liquid inside the mason jar, and it would have to be 79,432 kilograms per meters cubed, and that's equivalent to 5.84 times the density of mercury, one of the heaviest liquids. So quite a lot.